In our first example, we're going to consider carbon. This has 6 electrons. We want to figure out which atomic orbitals these 6 electrons will occupy. There are 3 rules that we're going to follow in order to determine that. The first rule is something called the Aufbau principle, which says that we're going to start by filling the lowest energy orbitals first. So for example, let's consider a system that has 1 electron, and we're going to put it into an energy diagram where we have to choose between putting it in a 1s and in a 2s orbital. The Aufbau principle states that you must put the electron into the 1s orbital. You start with the lowest energy orbital first. You cannot put the electron into 2s while leaving the 1s orbital vacant. That is incorrect. Don't do that. When I think of this rule, I think of the song Started from the Bottom, Now We're Here by Drake, because it kind of explains how you're filling the orbitals here, right? You're going to start from the bottom and then work your way up to there. Second rule is called the Pauli exclusion principle. The Pauli exclusion principle has 2 parts to it. First part is there is a maximum of 2 electrons per orbital. That is the maximum occupancy of an orbital. The second part of the rule is that if you have 2 electrons in an orbital, one must have its spin up, ms of plus 1/2, and the other one must have spin down, ms of minus 1/2. 2 electrons cannot occupy the same space at the same time with the same spin orientation. So that's an important thing to keep in mind. Let's see this rule put into action here. We're now going to consider a system with 3 electrons. We're going to put it into the orbital scheme here where we have a 1s and a 2s orbital. The Aufbau principle says that we start with the 1s orbital. So you could put the first electron there, and if the first electron has spin up, then the second electron that goes into 1s must have its spin down. The Pauli exclusion principle also now stipulates that this orbital is full and no more electrons can go in there. You now have to go on to 2s, and the third electron will go into there. I don't care if you put it with spin up or spin down, but that's how we would draw it. This is correct. Now, when I think of this rule, it kind of reminds me of Gretchen Wieners from Mean Girls. And here's why. Let's pretend instead of electrons, we'll think of people that are sitting at cafeteria tables at lunch in their high school. And we have our first person come in and sit down at the table. Second person comes in and sits down at the table. The third person comes in and they're not wearing pink on a Wednesday. Maybe they wore sweatpants for the second or third time this week. Maybe they made out with a hot dog. I don't know. But these electrons in the 1s orbital say to the third electron, you can't sit with us. And not allowed to go into this orbital, not allowed to sit at our table, and they have to go somewhere else. Go and eat your lunch in like the bathroom or whatever. That's the idea behind that. That's kind of what it reminds me of. I sometimes like to throw in pop culture references to make things a little bit fun and to kind of visualize what's going on a little bit here. Now, let's take a look at some things that would be wrong. So, you cannot draw a diagram that looks like this, where you put both of the electrons in the 1s orbital with the same spin orientation up. That would be incorrect. And it would be really wrong if you did this, putting all 3 into 1s. Definitely don't do that. Like, no, do not do that. Third rule is called Hund's rule. This comes into play when you have multiple orbitals that are equal in energy. And when you have multiple orbitals that are equal in energy, your goal is going to be to maximize the number of unpaired electrons, meaning that you're going to have to spread the electrons out into all of these equivalent energy orbitals. All right, let's just see an example of this. So we're going to consider a system that has 2 electrons, and I'm going to put it into a p subshell. Remember, p orbitals come in sets of 3. So with these 2 electrons, I'm going to put the first electron into one of the orbitals, and then the second electron is going to have an unpaired spin, meaning that if the first one is spin up, then the second one also is going to have spin up. But I can't put it into the same orbital because if I do that, it's going to violate the Pauli exclusion principle. And so the second electron has to be put into a different orbital here, also with spin up. So Hund's rule says that we're maximizing the number of unpaired electrons. Just like that. You could also have put it into this orbital and it would be fine. You could also have them both down in different orbitals and that's fine. But the important thing is you're going to spread the electrons out into different orbitals and give them all the same spin orientation, just like that. It would be incorrect to do it like this, where you pair both of the electrons up in this p orbital instead of spreading them out. So don't do it that way. This rule reminds me of riding on a public bus. So let's say that I get on the bus and I'm the first person on it. And so there are a ton of empty seats, right? Kind of like this situation here. There's a ton of empty seats. And so I go and I take one of the seats on the bus. We then get to the next stop on the route and another person gets on the bus and they have so many other choices of vacant seats that they can choose to sit in. If I don't know this person, then where are they likely to sit? Hopefully not right next to me, right? Because that would be kind of a weird thing to do when there's so many other empty seats on the bus, right? You would go and fill some other seat. Like, stay away from me. I like my personal space, and electrons like their space as well. So that's the way that we do it, right? We're not going to pair people up while still leaving a bunch of empty seats. All right. Additionally, there's one more thing to mention regarding the energies of the orbitals when we're talking about multi-electron systems. You saw previously that in a one-electron system, all orbitals that have the same principal quantum number are equal in energy. However, this changes for polyelectronic systems. Just by virtue of adding a second electron to the system, this will cause the energies of the orbitals to be split not only by their n value, but also by their L value. And the higher the value of L, the higher the energy of the orbital. Let's see what I mean by that. If you were to look at the energy diagram for a polyelectronic atom, you would see the following. For one thing, the n equals 1 shell doesn't change, right? Because you only had an s subshell here. But for the n equals 2 energy level, you have s and p subshells. In a one electron system, they're equal in energy. But in a multi-electronic system, they're going to be split based on the L value. The higher the value of L, the higher the energy of the orbital. So for 2s, s has an L equals 0, and for p, that has L equal to 1. So that's why the 2p subshell is higher in energy than the 2s subshell. In the case of the n equals 3 energy level, we have an s, a p, and a d subshell. And again, you increase the value of L and you increase the energy of the orbital. So when you have s, that's L equals 0. That's the lowest in energy of the n equals 3. Then for p, that's when L is equal to 1. So that comes next. And when L is equal to 2, the d subshell is even higher in energy. It's so much higher in energy, actually, that its energy exceeds that of the 4s subshell. So when the time comes for you to put electrons into orbitals for a polyelectronic system, you have to keep this filling order in mind. The Aufbau principle says that you have to start with the lowest energy orbitals and then work your way up. And so you're going to have to go in order of the energies of the orbitals, starting with 1s, then going to 2s, then going to 2p, then 3s, then 3p, then 4s, and then 3d, and so on. All right, so with that in mind, let's put the 6 electrons from carbon into these orbitals. So we're going to start with the lowest energy orbital. That's what the Aufbau principle says. And the Pauli exclusion principle says that you could put 2 electrons into that orbital, 1 up and 1 down. All right, from here we have to keep going, because we've only shown 2 out of 6 so far. So now we go to 2s, and so we could put in 2 more electrons, and now that orbital is full. I've shown 4 so far, and again, I'm trying to get to a total of 6. So the last 2 electrons will go into 2p, and Hund's rule says that we're going to spread them out into different orbitals and have their spins unpaired. That would be what the orbital energy diagram would look like for carbon, where you have 6 electrons. Then we could write what's called the electron configuration for the carbon by indicating what orbitals are populated and how many electrons are in each orbital. So what we can say is that, well, we have a 1s orbital that's populated, and there are 2 electrons in it, so a superscript 2 will indicate those 2 electrons. Then we've also populated a 2s subshell, and we have 2 electrons in there. And then we also have a 2p subshell that's populated, so we'll write 2p, and there's 2 electrons in there. That is our electron configuration. Now, you don't have to memorize this filling order, right? You don't have to memorize the order that the orbitals go in. There is an easier way to determine it that doesn't require memorization, and it comes from decoding information on the periodic table. It is truly remarkable how much information is encoded within the periodic table. When Mendeleev came up with it in the 1860s, electrons hadn't even been discovered yet. But somehow, the way that he organized the elements on the table, he was able to encode tons of information about electrons and the orbitals that they occupy. It really is remarkable. In the periodic table, it's broken down into 4 blocks. And you'll see that if you look at the information page. The first two columns are called the S block. These 6 columns on the far right-hand side of the table are called the P block. The area in the center of the periodic table where we have the transition metals is referred to as the D block. And this bonus region of the periodic table where the lanthanides and actinides are is referred to as the F block, where you have F orbitals and F electrons. Interestingly here, S orbitals always come in sets of 1, and you can put a maximum of 2 electrons into that S orbital. And there are 2 columns here representing 2 electrons in an S subshell. For a P subshell, P orbitals come in sets of 3, and you could put 2 electrons into each orbital, giving you a total of 6 electrons that can go into a P subshell. When you look at the P block, there are 6 columns here. For D subshells, you have 5 orbitals, and 2 electrons into each means 10 total electrons can fit into a D subshell. And when you count this out, you'll see that there are 10 columns in the D block to represent 10 electrons. And F orbitals come in sets of 7, 2 electrons each gives you 14, and there are 14 squares, or 14 columns in the F block. It's really amazing what information is in here. Now, in addition to that, what you can do is label each of these blocks. What I recommend doing is putting a 1 at the top of the S block, a 2 at the top of the P block, a 3 at the top of the D block, and a 4 at the top of the F block. Those represent the minimum value for the principal quantum number that a given subshell could have, right? S orbitals start at n equals 1. P orbitals don't start until n equals 2. D orbitals don't start until n equals 3, and so on. From there, you can count down the rows of the periodic table. So 1, 2, 3, 4, 5, just like what you see in the slide here. Now what you can do is find the element that you're interested in. In this example, we were dealing with carbon, which is located right here. So we'll just kind of draw an arrow pointing to where carbon is. And then our goal is going to be to write the electron configuration for carbon by starting at the very beginning of the periodic table, where hydrogen is. When we start at the very beginning of the periodic table, we're in row 1 of the S block, and so that represents a 1s orbital. So we'll write 1s, and then we count spaces. We're going to count up until we get to where carbon is on the periodic table. We're in 1s, here's 1, and then 2 spaces there. So helium counts as part of the S block. 2 spaces, so that means 1s, 2. Then we drop down to the next row of the S block, which is row 2 of the S block. So now we're going to say this is going to represent the 2s subshell. And then we count over 2 spaces, 1, 2, and then we get to the end of the S block, and so that represents the 2 electrons that go into a 2s subshell. So 2s2. Then we continue on, and as we continue on, now we enter the P block. We're in row 2 of the P block. We labeled it as such. Now to get to carbon, we have to count over 2 spaces, right? Here's 1, 2 to get to carbon. So that represents 2 electrons. So in this 2p subshell, I'll put 2 electrons. And that gives us the configuration 1s2, 2s2, 2p2. This is another way that it can be done without having to draw out the whole energy diagram and without having to memorize the filling order. The periodic table will tell you what the filling order is, so you don't have to memorize it. Now, having written the electron configuration for carbon as 1s2, 2s2, 2p2, I do want to point out that there is a shorter notation that you can use, and it follows the following convention. You'll find the element that you're interested in, and then count back to the first noble gas that you find. In this case, it would be helium. Let's take a look at a periodic table. So here we have carbon, and we have to count backwards to the first noble gas that we find, and when we go back, we get to helium. All right, so we found that helium is the first noble gas that you find. You're going to write helium in brackets. So He in brackets. And what that represents is the first 2 electrons in the configuration for carbon. Then we'll write whatever comes after helium from there. So after helium, let's go back to the periodic table and take a look. After helium, we drop down to here, which is row 2 of the S block, 2 spaces, so that's 2s2. And then we enter the P block, and we're in row 2 of the P block, so 2p2. So then we would write 2s2, 2p2. And that's maybe a shorter way of writing the electron configuration. I recognize that for carbon, it doesn't really matter a whole lot because, the first noble gas that you find is helium, which only represents 2 electrons. But as you start dealing with elements that are further down on the periodic table, you can write noble gases in brackets that can represent way more electrons than that, and you can save yourself a lot of time. And in our next video, we're going to take a look at some more examples, and you'll see how it helps to use the shorter notation.